All right, folks, let's get started. Welcome to the Apache Sedona Community Office Hour on September 3rd. And this is Jia. I'm the PMC chair of Apache Sedona. So, as usual, let's quickly go through what Sedona is for people who first time attending the office hour. So, Sedona is an open source cluster computation engine for processing big geospatial data. And we have our source code hosted on GitHub. It is under Apache organization. We also have our website at sedona.apache.org. We also have Twitter account, and we also have our LinkedIn page. So if you're interested, please follow us on Twitter and LinkedIn to get the latest news. The status of Apache Sedona. So as you can see on your right-hand side, so there are many companies are using Sedona right now. And Sedona is a project started in 2015, and it became mature in 2017, and it joined Apache Software Foundation in 2020. And right now, it has over 10,000 corporate users and being used by many companies, as you see on the right. On GitHub right now, it has over 120 contributors and actually 1,900 stars on GitHub. It has over 1.5 million downloads last month, and overall it has 34 million downloads. This places Sedona on among the top 0.3% most downloaded packages on PyPy. So many people and many companies are using Sedona. So a quick overview about the system architecture of Sedona. So as you can see on your right, Sedona is a very complicated system, and it has also well integrated with the whole ecosystem. So on the top, Sedona has a spatial query processing layer. On this layer, so we provide Scala Java interface, spatial SQL and Python, as well as R API for our users. And in this layer, we also provide a bunch of distributed query algorithms, including range join, range query, KNN query, join query. And we recently also added the k-nearest neighbor join query. I will talk about that later. We also have raster capability like raster map algebra, NDVI, and masks. And most importantly, we have our spatial query optimizer. So that means it will automatically detect what the best algorithm is for this particular query, and it will automatically choose that one for you. So from the user side, all you need to care is the spatial SQL query, right? So we will figure out the best algorithm for you. The second layer is the distributed spatial dataset layer. So in this layer, it actually contains multiple functions that actually partition and prepare data structure for spatial data in a distributed environment. So that includes spatial partitioning, spatial indexing, and spatial data compression. So as you can see here. So at the bottom, Sedona run on top of a number of different distributed engines, includes Apache Spark for batch processing, Apache Flink for streaming, as well as Snowflake for batch processing. And among these engines, our support on Apache Spark is the most comprehensive one. And so if you want to try Sedona, the easiest way to get started is to use our Docker image. So our Docker image is a single host self-serving tool for you to play with Sedona. So you can go to our Docker Hub image. So there is an official Sedona repository on Docker Hub under the Apache Software Foundation. You can pull the Docker image there and you can try it out. Our Docker image has a Jupyter Notebook interface using Python. You can directly run it and start to play with it. It also have a number of notebooks bundled inside this image. You can directly try that. without actually having any deployment yourself. All right, so Sedona releases. So as you already know, Sedona is following the 3 month release cadence. So we publish a bunch of release in 2024. So 151, 152, 153. Recently, we made a new release 161 in I think last week on August 24th. And this release is a maintenance release, which means that the API is mostly stable for this release. We only focus on adding non-breaking changes and also like relatively small changes and features to Sedona. So let's also take a look at what's new in Sedona 161. So first of all, in Sedona 161, we have a native GeoJSON reader and writer. In the past, Sedona has been able to read and write GeoJSON for a very long time, but the reader and writer we had before, it was written in the RDD API way. So that means it has a few drawbacks. So you need to load the GeoJSON file using the RDD API. And once you finish that, you need to convert that to the data frame API, use our adapter. So in the meantime, you will lose the data types. And also it is not well structured for the JSON format. And also it does not well support the multi-line JSON file. So that's why we are introducing this native GeoJSON reader and writer. It is built on top of the data frame API and the SQL table API in Spark. So as you can see here, you can easily read a GeoJSON file using this reader API, Sedona.read format GeoJSON. You will be able to load multi-line GeoJSON and also single-line GeoJSON. Also, as well as feature collection. If you use GeoJSON before, you can read feature collection. You can also read feature. For example, the one on your right. So this is an example of a multi-line GeoJSON. So it means that in this GeoJSON file, a single record, in this case, this record is a feature collection. So this is a single record. This entire file is a single record called feature collection. So this record cross multiple line, right? So this is called multi-line JSON. And there are also ways that you can actually put this entire thing into single line JSON file, right? Which is not easy for human to read, but that is actually easier for the system to process, for distributed system to read. But anyway, so this is an example for the multi-line GeoJSON. You can easily read it back, right? And the resulting format will be something like that. You can also elevate this column to an upper level, so on and so forth. You can also write GeoJSON using the same Sedona dot. You can use the same data frame dot write dot format GeoJSON. You can save it to the path you want. Another new feature we added in 161 is the GeoParquet 1.1 covering column support. So covering column is a feature introduced by GeoParquet 1.1 spec. So in particular, what it adds is it adds a covering column to the table you have. This covering column has a nested structure. It has at the moment it only allows bbox. So in this bbox covering column, you can have 4 attributes: xmin, ymin, xmax, and ymax. So this will help you to perform filter pushdown without actually being able to read the WKB format. As you probably know, GeoParquet encodes GeoGeometry in the WKB format, and it is actually also compatible with any Parquet reader, right? However, the original Parquet reader So it does not understand WKB format. It won't be able to perform filter pushdown at the row group level and page level. So with the help of the current column, as you can see, the current column only contains primitive types supported by Parquet. So that means even use a regular Parquet reader, you can perform filter pushdown on the geometry data at the row group level and column level. So that will give you much better performance. However, there are some drawback in the current column. So that means the current column is only a recommended option. It is totally up to the user to decide whether we want to include the current column or not. So the drawback includes more storage overhead. Imagine that you have a geometry column that only has point data. So this point data only has two fields, X and Y, right? Now, in order to perform efficient filter pushdown, you are adding this current column which contains four fields for the same data. That means you are paying extra overhead for the geometry data. So in addition to two XY values, you are now having 6 values with 4 additional fields. So you're paying extra storage overhead. So it is actually up to the user to decide whether this is worth it, right? Whether you prefer better filter performance or you want to save some storage or save some storage. And another new feature we have in 161 is we added over 50% new ST functions. So that brings Sedona now the most comprehensive cluster computing engine that supports geospatial data. So in 161 release, Sedona vector geometry function, the ST functions, reached 193 functions in total. And the Sedona raster functions, so the function that with the RS prefix, now reached 97 functions in total. So this is very comprehensive support, and I believe it can cover the vast majority of the use cases. Cool. So this is about Sedona 161, and this release was already published. So if you are interested, please feel free to try it out. And now let's talk about what we're going to have, what we plan to have in Sedona 170. So 170 is a major release, so we expect that to happen in about 2 to 3 months. And in Sedona 170, we are looking at several major changes to the project. So the first thing we are introducing is a new spatial join tab. This is the first spatial join tab we have ever had since 5 years or 6 years, right? So this is called distributed k-nearest neighbor join. So I believe you guys have been really familiar with the k-nearest neighbor query, right? You are looking for, so given a query point, you are looking for the k-nearest neighbors around this query point, right? So the k-nearest neighbor join is actually extending this concept to a number of, to hundreds of thousands of, even millions of query points. So basically, since this is a join query, it involves 2 data sets, right? So for each record in the first data set, it finds the k nearest neighbors from the second data set based on a given distance metric. So distance metric could be Euclidean distance. It also could be spherical distance, like meter distance, right? So the support of this join query has been merged to the master branch of Sedona on GitHub. And that means it will be added for sure. So it has the following API for user. You can use select from select from clause, you can use the join operator. The join condition here is st. We call it st KNN. You can put two columns inside this function, and this will actually give you a result similar in the format similar to spatial join query. So basically, on the left you have the query points. On the right you have the nearest neighbor you find for this data. So there are a few really interesting real-world applications for k-nearest neighbor join. So for example, this screenshot was taken from Redfin, right? You can use k-nearest neighbor join to find the public school, say the nearest 5 public school around each of the property. So this will be really helpful for real estate companies to find the resources around the property. Another good use case for the k-nearest neighbor join is something like reverse geocoding. So suppose you have a bunch of coordinates, and you want to find the address for each of the coordinate. So this is oftentimes called reverse geocoding. So what is behind the scene is, so usually you need to join those coordinates with the address mapping table. So this address mapping table usually contains 2 columns. An address column that contains the street address, and another one is coordinate column that contains the coordinate that is associated with this address. However, those coordinates of the addresses won't directly match the input coordinates of the reverse geocoding problem. You need to perform a reverse geocoding algorithm. You need to perform a k-nearest neighbor join algorithm to find the nearest address for each of the input coordinates. So reverse geocoding could be a really good example for the distributed k-nearest neighbor join. So here let me introduce a little bit about how we achieve the distributed k-nearest neighbor join. So in the distributed k-nearest neighbor join, similar to the regular distributed spatial join we have in Sedona, so we also perform this thing called spatial partitioning on both sides of the join, right? However, the k-nearest neighbor join is much more complicated compared to the spatial join, because considering that the case neighbor of the query point could be very far away from the original query point. It might not be even in the same partition, of the query point. So in order to guarantee the correctness of your query, so we need to make sure that we are able to find where the case neighbor is, right? So actually that requires us to perform one more round on the spatial partition result to actually add a buffer region on the query side of the join. So this buffer region makes sure that the partitioning of the query side always cover the possible partition that contains the case neighbor, to make sure we always give you 100% accurate result. It is also worth noting that the distributed k-nearest neighbor join we have in Sedona this time is very different from any existing k-nearest neighbor join available in other cloud data warehouse vendors. So as far as we know, the other alternatives on the market, they mostly use regular spatial join to simulate the k-nearest neighbor join. That is, so they start with the minimal distance as the run join. like as a distance threshold of the range join, and see if error point within this distance can find the case neighbor. If not, this algorithm double the distance, for example, try to locate the case neighbor. If not, it increase the distance radius again. So essentially, this use the regular distance spatial join to simulate the k-nearest neighbor. And this process is an iterative and hit or miss process. It is really time consuming. And in our distributed KNN join, so we are not using this kind of iterative method. We are using a new and different algorithm to find the accurate result for the query. All right. So another important functions we plan to add into Sedona 170 is the statistics functions. This is also important. Some function has been asked by the community for a very long time. So the first statistic function we plan to add into Sedona is dbScan clustering. So this is probably one of the most popular clustering function available in the industry, and many users in Sedona community has been asking for it. So essentially, the dbScan clustering function we plan to add into Sedona 170 is to support clustering based on spatial proximity. So it means that given a bunch of spatial data points, spatial objects, we want to make sure that we partition data based on we cluster data based on their spatial proximity. So nearby records are put in the same cluster, given a certain distance threshold. So the implementation of this function is mostly complete. We plan to merge this to open source Sedona in a few weeks. So on the right, you can see this is actually a result of our preliminary implementation of the clustering dbScan clustering function. So this is a clustering on top of the real estate properties in Florida. As you can see here, each of the blue polygon is actual cluster of the dbScan. They can nicely cluster data based on their spatial proximity. And most importantly, the dbScan clustering algorithm we're adding to Sedona is the distributed dbScan clustering function. So it is very scalable and also run on top of cluster. The second statistic function we plan to add into Sedona 170 is called hotspot analysis. So the goal of this hotspot analysis is to find statistically significant hotspots of a dataset. It is worth noting that the hotspot analysis we're adding here is really different from the traditional aggregation-based hotspot analysis. I believe you guys have been seeing people doing lots of heat map or aggregation based on H3 grid or other kind of H2 grid, simply by counting how many records inside each of the H3 cell. So that is actually very simple and probably also efficient algorithm to calculate aggregation. However, the hotness indicated by each cell in that approach does not necessarily indicate that this hotness actually representing the actual whether this cell is actually a hotspot, because you are not eliminating the randomness factor in this process. So there are lots of outliers and randomness factor involved in this kind of spatial analysis, right? So that means you cannot 100% safely rely on the result of that kind of hotspot analysis to make decision. So that's why in Sedona 171, we're adding a more scientific proof, uh, scientific proved hotspot analysis function. So the result it produced shows that all the hotspots are statistically significant hotspots. We're using a metric. We're using a metric called GetXOR, to calculate the hotness of each cell. So essentially, what it does is it actually tries to eliminate the randomness factor of the result. So that means the output you can rely on the output to make decision. So on the right hand side, you can see an actual output of the hotspot analysis of our initial implementation. So although it looks similar to the traditional count-based spatial aggregation method, however, the hotness here it also comes with a z-score. It also comes with actual value, hotness value. So you can use that to make decision to measure the hotness of each cell. So we plan to merge this function very soon to Sedona in a few weeks. All right, so that's about the 170 release. As usual, so the Sedona community is always call for help. So you can always contribute to open source Sedona by adding more notebook examples to help other users to get familiar with Sedona and know how to apply Sedona to their own use cases. And we also welcome documentation update, right? So if you see there is a typo on the documentation website, if you see there is if you see there's something you want to add, some tutorial you want to add to the Sedona website, you are welcome to do so. We also welcome release test. So not sure if you guys are aware of this. After each release, before each release, we always perform a release test. We always call for a vote on Sedona mailing list. So by the way, we have a mailing list for Sedona. So the committee member will start to perform test on the release and make a vote, cast a vote before we actually publish a release. So you're also welcome to participate in the release test to make sure there's no obvious bug in the release. All right, so that's all for the office hour today. Now let's start the Q&A session. So we see there are a few members, community members on the call. So I'd like to invite you guys to raise any questions if you have, and I'd love to hear that and answer. Hi, folks. Do you have any questions you want to ask? Hi, Thomas. Do you have any question?
Hey there. No, nothing off the top of my head, I don't think. Excited about the new features though.
Great. Yeah. Do you mind introduce yourself? I think I met you before, right?
Yeah, I've popped into these several times. Yeah, I'm Thomas Carter. I'm a data engineer, doing a decent amount of spatial data stuff right now. I work for an ad tech company, so we have a whole lot of spatial data we deal with.
Great. Yeah. Glad to know that. And please feel free to reach out to us if you have any questions.
Absolutely. Thank you.
Tim, do you have any question?
No, I really appreciate the presentation.
Thank you. All right, folks. So yes, I think that's it for the office hour today. If you don't have any question, please feel free to leave. Otherwise, I will stay here and see if you guys want to chat.